How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at some calorimetry of phase changes. So objectives: calculate the changes in energy for heating substances as well as the heat changes associated with changes in phase. So we're talking about heating stuff up as well as melting it, freezing it, as well as boiling it and condensing it. All right. Chemistry reference tables. The ones that we're going to take a look at is on the front page. There is table B, physical constants of water. We'll need to refer to these, as well as on the very back page we have equations, and we're going to look at the one for heat. All right, so heat of fusion. Hopefully when you hear fusion you think of like solid things being stuck together. So that is when you're going to use it, whenever there is a solid present. So we can be going from solid to liquid or liquid to solid. You're going to want to use the heat of fusion. Vaporization. Hopefully you're thinking of vapors, and there's a vapor present when you're using this. So either from liquid to gas or from gas to liquid. We're going to be taking a look at these numbers. Now this right here is when it's just water, specific heat capacity of H2O liquid, just water. So we look at table T. We got three different equations, right? When will we use each of these? Well, let's take a look with what they even mean. We got Q equals MC delta T. Notice the M means the mass. So whatever it is that's changing temperature, we want to know the mass of that. You know, what is the stuff we're talking about? Big C is the specific heat capacity of water. That is this right here. You know, if on your reference tables you wanted to write C, that's what it is. What else we got? Delta T tells us is the change in temperature. And then let's see, we got Q again means heat. We got M again means mass. And H subscript F, what's that mean? The heat of fusion, which is right here, right? This is your HF. And then here we got another one, looks the same except it's H subscript V for heat of vaporization. And that is this one right here. All right, so when do we use these formulas? When is it appropriate to use the Q equals MC delta T? You're going to use that when there is one phase present. The temperature is changing and there is no phase change. So that's when you want to use this one. Hey, is it one phase? Use that. Is the temperature changing? Use this one. A special note, that value for C in the MC delta T depends on the substance and what phase it's in, right? So most of the time, our go-to is going to be this liquid water. We're going to use that one all the time, and it's on the front page. You don't got to memorize it. It's 4.18 joules per gram Kelvin, or joules per gram degree Celsius, which it's the same thing. If I change temperature 1 degree Celsius, I've changed 1 Kelvin. But if the same substance but is in a different state, like a solid, like ice instead of liquid water, then the value will be different, and it's usually will be given to you in the problem, all right, or given to you in the problem. Now, when do we use the Q equals MHF or the Q equals MHV? We do that when there's two phases present. The temperature is going to be constant, which is why there's no like delta T. The temperature is not changing because it's going through a phase change. All right, another note. The value for H depends on the substance and what phase it's going through. Most of the time, we'll be dealing with water. So if it's melting or freezing, you use the HF. If it's boiling or vaporization or condensing, you use the HV value, which you can find on the front of your reference tables. All right. So taking a look at this heating curve, when would we use each formula? Well, let's take a look. In this first section, I have only a solid, and it's changing temperature. So in this section right here, if I'm trying to solve for the amount of heat associated with that, I'm going to use the Q equals MC delta T. For this flat part right here, well, hey, it's flat. There is no delta T. So I know I'm going to have to use the Q equals MH. And then, what's going on here? Well, it's going from a solid to a liquid. So I'm going to want to use the Q equals MHF. All right. In this section where it's like, hey, this is just liquid. I have just a liquid that's being heated up. Oh, we got a change in temperature. We're going to want to use the Q equals MC delta T. All right, another flat section where I have a liquid going to a gas. I'm going to want to use the Q equals MH in this case because it's going to a gas, HV. All right, once I have only gas present, this section, and the temperature's changing again, I'm going to want to use the Q equals MC delta T. Now the values for C in these sections are all going to be different. All right, most of the time we're going to be taking a look at the liquid part. So this is going to be our go-to, whereas the C value is just off the front of the reference table. Other things to note, watch out for distractors. And what I mean by that is pieces of information that you don't actually have to do anything with. For example, the question might say, well, what is the change in heat for a 10-gram sample of ice melting at 0 degrees Celsius? That 0 degrees Celsius just tells us we didn't have to heat up the ice to get to the melting point. It's at its melting point already. It's just going through a phase change. So we won't actually use that 0 degrees Celsius at all. We'll just use the Q equals MHF, where the mass would be 10 grams. I think the HF, let me go back instead of guessing. Yeah, 334. So we got 10 grams times 334 joules per gram. And that'll give me, hey, grams cancels out. I end up with 3,340 joules. I didn't have to use that 0 degrees Celsius in my math at all. It's just letting us know we're starting off at the melting point. We don't have to do anything with the 0 degrees Celsius. So example problem, show a numerical setup for calculating the quantity of heat in joules required to completely vaporize 102.3 grams of H2O liquid at 100 degrees Celsius and 1 atmosphere. So this 100 degrees Celsius just tells us that we're at our boiling point. We don't have to heat it up to get to the boiling point. We're at our boiling point. There is no change in temperature. This 1 atmosphere is distractor stuff. It's just telling us it's under normal pressure. All right, well, let's see. Which equation? I don't have a change in temperature, so I know it can't be this MC delta T. And I have it vaporizing, so I'm going to want to use this one. So I use Q equals MHV. Now I can plug in my numbers. Well, what is my mass? My 102.3 grams times my HV, which I look on the front of my reference tables. There it is, 2,260 joules per gram. My grams cancels out, and I now have my numerical setup. I didn't even want the answer. There it is. That's my numerical setup. All right. Here's another example. Which numerical setup? I'd change it. How about show a numerical setup that can be used to calculate the heat energy required to completely heat 100 grams of H2O liquid from 10 degrees Celsius to 45 degrees Celsius. Oh, we got a change in temperature. That tells me I'm going to have to use this MC delta T. So Q equals MC delta T. All right, well, my mass, they said 100 grams, so 100 grams times my C of liquid water, specific heat capacity of liquid water, times 4.18 joules per gram Kelvin, times, my delta T. Hopefully you know how to just show the change in temperature. So final temperature minus initial temperature. So 45 degrees Celsius minus 10 degrees Celsius will get me my temperature change. That's all this problem would be asking for. All right, you could have also done, hey, let me just show 35 degrees Celsius as my temperature change, and have been done with it. All right. All right, summarize. Can you calculate the changes in energy for heating substances as well as heat changes associated with changes in phases? All right, I hope you found that helpful. See you in class. Okay, bye.